Okay. Uh, Now 4 p.m. in Japan. So it's time to start the webinar. Good evening and good morning, everyone. Thank you for coming to this webinar, Six Frontier of Concrete Technology. I am Koji Terasawa from Osaka University, and I am in charge of today's moderator. The title of this webinar is Prospective NDT Non-Destructive Test for Civil Engineering Materials and Structures. And this webinar is organized by JSCE, Japan Society of Civil Engineers, and supported by FIB, Japan Young Members, and JSNDI, the Japanese Society for Non-Destructive Inspection. This is today's schedule. At first, I would like to introduce about JSCE. After that, a presentation from two invited researchers, Professor Aggelis and Professor Shiotani, will be held each for 30 minutes, and we take some time to have a short Q&A for each presentation. After these presentations, a panel discussion will be held. And last, in the closing, I would like to announce the information about the next seminar and questionnaire and certificate of attendance of this webinar. Before starting the webinar, let me explain some information for all participants. For Q&A from audiences, now we have more than 50 participants, so it is difficult to handle all questions from audiences directly. And so I would like to the audience to use the Q&A function of Zoom, Q&A box. If you have comment and question, please write it with your name and your affiliation in the Q&A. Some of the questions and comments will be selected to answer from invited researchers and to deepen the discussion in panel discussion. So please write your question in Q&A aggressively. Now, this seminar is also broadcast on YouTube live streaming, but it doesn't work. Okay, and the past FCT seminars have also been uploaded to YouTube channel of JSCE. So if you are interested in, please check it. Okay. Let's move on to introduction of JSCE. JSCE, Japan Society of Civil Engineers, was founded in 1940. Long history, more than 100 years, to contribute the advancement of scientific culture by promoting the field of civil engineering and the expansion of civil engineering activities. And now there are approximately 39,000 members, including student members. You can check the latest activity of JSCE from webpage, Facebook, and IAC News International Activity Centers, and so on. And JSCE has several research committees, and one of them is a concrete committee. This concrete committee published a standard specification for concrete structures in English. You can download this specification freely. So if you are interested in, please check it in JSCE webpage. In addition, we have issued a newsletter every 3 months about latest activities. And today's report will be on this newsletter. Also, we are doing the international seminar almost every year with Asian countries, sometimes with European countries. And this webinar is one of such activity of concrete committee. Okay. I would like to finish introduction of JSCE, and let's move on to the main part of this webinar. The next content is presentation from invited researchers. Today, we invite two leading researchers in the field of NBT applying to civil engineering materials and structures. Presentation time is about 30 minutes. And before starting each presentation, I'd like to introduce the invited researchers. Okay. First invited researcher is Professor Dimitrios Aggelis with the Department of Mechanics of Material and Construction at the Vrije Universiteit, Brussel, Belgium. And he has many research achievements and contributions, so I cannot explain all of his biography today. So I will introduce the selected biography. She is active member of several technical committee of LILEM, the secretary of 269 IAM, and damage assessment in consideration of repair, profit recovery in, and was in concrete and masonry structure by means of innovative NDT, chaired by Tomoki Shiotani. He is also today's invited researcher. And she was a recipient of the William Robert Hermit Medal of 2020 for his contribution in the field of construction materials. He is editor-in-chief of the journal Development in the Built Environment, editor of journal Construction and Building Materials, the acoustics section editor-in-chief of Applied Sciences, associate editor of Material and Structures, editor in Sensor, and additional board member of NBT and E International. He is author of more than 160 journals and 200 conference papers. Okay. His main area of interest includes characterization of cementitious materials, expanding also to composite and metals by use of non-destructive inspection technique for focused on elastic wave propagation. Okay. Today, the title of his presentation is Elastic Wave from Monitoring of Structural Material Performance. Okay, Professor Aggelis, could you share the slide?
Yes, I will share the slide. Can you all see the slide, the presentation?
Yes, okay. Oh, okay, could you start your presentation?
Okay, so thank you, Professor Terazava, for the introduction, and of course for the opportunity to participate in this very interesting series of webinars organized by the Japanese Society of Civil Engineers. I am Dimitrios Aggelis from the Department of Mechanics of Materials and Constructions of the Vrije Universiteit Brussel, and I will discuss about elastic waves, that is basically ultrasound for monitoring of structural materials performance. Initially, I was optimistic that I could also include passive approaches like the acoustic emission, but in the time frame of 30-35 minutes, I decided only to talk about active approaches, that is ultrasound eventually. Since this is organized by the Japanese Society of Civil Engineers, I could not resist but to give a throwback slide from the time that I used to be in Japan when I participated in a couple of annual meetings of the Japanese Society. This is, for example, from 2006 in Kusatsu, Shiga. You see that at that point, I was much thinner, obviously, with more hair. But one thing that didn't change is that I always occupied with non-destructive testing with some kind of elastic waves. Another thing that didn't change is the appearance of Tomoki Shiotani, who is exactly the same as he was. So we cannot see any deterioration in him, like in the materials and all the other people. So I will start as we try to warm up with a slide that we use a lot in that RILEM committee that you already mentioned in my description, where we talk about maintenance and repair and, of course, non-destructive inspection of structures and materials. So here, basically, you see the performance of a structure or the quality level versus the time. Obviously, when it starts, it has the maximum level. It will never go higher than that. It can only deteriorate with time, as we understand. If we allow a lot of deterioration to happen and it loses functionality, then of course we have two choices, either to renew the structure, so build a new one. That would mean, of course, a lot of burden, economic burden, a lot of human hours, burden for recycling the material of the previous structure, but it is a legitimate choice and we can always do it. So we extend again the quality for another big period of years, like 30 or 50 years. But we can also have the choice to repair. In that case, of course, if the damage was already extensive in the structure, even the repair is good, still it cannot reinstate the quality to the top initial level. Therefore, it is a legitimate choice as well, but of course, it just extends the life of the structure for some time, which can be also very crucial. Now, there is also the possibility that we can do some kind of maintenance action earlier than that to be proactive. In this case, the quality of the structure has not dropped dramatically. We can still use the structure, but it's easier to repair small-scale damage, small cracks, for example, and we can again achieve the same level of quality that was from the original application of the structure. So in this case, you need to have some kind of sensitive non-destructive testing technique in order to realize, to characterize the damage even before it becomes too obvious in order to create problems in the structure. Apart from that, you also have the initial part, the initial quality, which is also crucial. If the initial quality of the structure is high enough, then even with some kind of deterioration, it will still be possible to use the structure for a long time. Therefore, in this area, of course, initial material evaluation, as well as the damaged state of the structure, non-destructive testing plays a very important role. I will focus more on this type of stage, let's say. I think that Tomoki will also talk for more damage and for more structural applications. So, since I will talk about elastic waves, I show this slide. This slide, I also have the copyright because it belongs to my son. It is the echogram just before being born, maybe a couple of weeks. And then this is how he turned out to be a couple of weeks later. So you see that there is a very big resemblance, and that shows us that the ultrasound, of course, apart from being non-destructive because we also use it for our own health and our own body, it can also give you a lot of information for a hidden target that we don't have direct access to it. This goes hand in hand, of course, with the characteristic of ultrasound that it is directly related to the elastic modulus of the material. If I measure the velocity of the wave, I can more or less calculate the elastic modulus, the stiffness, which is very, very important. And this can be for the longitudinal waves, or I can also find the shear modulus when I have shear waves. Therefore, I can characterize very well the stiffness of the material. Furthermore, apart from the stiffness, especially for concrete, there is the effort to characterize the quality and the strength of the material based on the ultrasound. It is even in the ASTM standards. So you see velocities more than 4,000 meters per second. They show a very good or excellent concrete. You can even project to the final compressive strength. Of course, if you have low velocity, then the quality is very poor and the strength is also very low. There is in general very good correlation, always positive correlation between the strength and the velocity, the pulse velocity. It's not a unique relation. It depends on the material type, on the conditions, the water to cement ratio, a lot of stuff. However, all the different researchers always find a positive trend between the strength and the velocity. And this is very helpful because as a measurement, ultrasound is not too complicated. If you go, of course, to a very big structure and you want to do a tomography, as you will see some examples later from Tomoki, I guess that this is more complicated. But if you just want to have an estimation of the quality of the material, you can just use your sensors and you can do a very fast measurement, which is quite reliable. It gives you the quality of the material in general terms. That's a very good piece of information, of course. Now, up to now, I talked about material that I didn't introduce much damage in it. So in this case, you do not have any effect of the frequency of the ultrasound, because even if you have short wavelength or large wavelength, there is no interaction with any type of heterogeneity of any microstructure. But of course, we know that this is not ideal. The concrete is not an ideal material. Therefore, this relationship is not always valid. And you have also the function of the frequency that plays a role, and you can use that in your advantage to make even more delicate characterization. So, as I said, we can do this measurement, which is quite simple. If you want to do just one measurement with a transmitting transducer and a receiving transducer, you know the thickness of your specimen. You can even have this as a handheld unit that you can go on the site and make measurements. But let's see what happens inside, considering that it is like a homogeneous ideal material. You have your pulsar, the wave propagates. This is just 4 snapshots of the wave until it reaches the other side. If you know the thickness and you know the transit time, because this is what you measure by your sensors, then you find the wave velocity. Now, in this simulation, you see that you have a longitudinal wave and a shear wave that are clearly separated with each other. So you can understand that one goes faster, the other goes slower. You also see maybe here some side reflections. Why is that possible? Because your frequency is quite high, and that makes a very short wavelength that it's easy to differentiate. Now I hear my voice.
Yes.
Let me see why I hear my voice.
Oh, I can hear your voice.
Wait.
Can you hear?
Okay, I think that now I managed to shut it down, and I guess that I can continue. So now you can see and hear me normally. Okay, can I continue? It's okay?
Yes, I can hear your voice.
Okay. So now I try to repeat the last thing, that we see the longitudinal and the shear wave and also the reflection. And this is possible because the wavelength is quite small, because we have high frequency. And therefore, the 2 wave modes can separate easily because they travel at a different speed. So it's easier to understand what's going on when we have a high frequency for a homogeneous material. If I had low frequency, and that means that I would have long wavelength, imagine that I would have something like that. It would not be possible to discriminate, to understand what's going on, because the wavelengths are too big and therefore they are overlapping. Therefore, this is one important point about the frequency, and especially in simulations, we usually apply first high frequency to understand better the mechanics of the propagation, to understand the different reflections, the different wave modes, and then, of course, we can go to a more realistic case that may have many more complicated view. So this is one point, but of course, this is only for ideal material. Now let's go to a material that starts being heterogeneous. So concrete, we know that it's very heterogeneous. It has aggregates in any case, but also it can have a porosity, voids, and extra damage. Here I show you two examples. One is with horizontal type of cracks, ellipsoidal voids. The other is with vertical. And if we try to apply a similar simulation like the previous, you will see that here it's not as clear anymore. It is much more mixed because of the multiple scattering of the wave. Even though it seems and it is more complicated, obviously there are still relations that they can take into account: the percentage of the scatterers, the impedance mismatch or the stiffness mismatch between the different components like the voids and the matrix and so on. And they can combine everything into what we call the dispersion relation that allows us to find again the velocity of the composite medium. So imagine that when you have an incident wave, it reaches your scatterer, that could be a void. The energy will be scattered to all the different directions. Of course, also forward scattered, maybe backward scattered in all the different angles. And if you take statistical considerations about the material, and you can change the volume content here, or you can change the size with R here. Of course, you can input the material properties into the wave number, that is the mechanical properties, as well as the frequency, of course, here. Then you can solve for the wave number of your composite medium. Therefore, from that, you can calculate the wave velocity and the attenuation, even in a very complicated scattering medium, and it works very well. This is just one of the dispersion relations. There are other, but all work quite well. Now, if I use this, I can predict what I would expect to happen from a material with certain characteristics. And now let's go to one example with some values. Imagine that I make this test that I showed you with a pulsar receiver, and I find the pulse velocity of 4,200 meters per second. If I consider my material homogeneous, as I said earlier, with this relationship, I can solve for the modulus, and I can calculate that it belongs to a modulus of 41 gigapascal. So this velocity corresponds to 41 gigapascal stiffness of material. For a concrete, I can assume a density, or I can anyway know the density of a concrete. Also, the Poisson is around 0.15, 0.2. Anyway, the interesting part here is the modulus. So I can calculate the modulus. In this case, the wave velocity would be constant for any frequency because there is no type of heterogeneity to interact with the different length scales, the different wavelengths. Obviously, you understand that this is just one theoretical case that of the many that can happen. And I can give you one example here, because you could have a material that is stiffer, like 47 gigapascal, but with 3% of voids. And then again, you will have the same velocity for a specific frequency, like 4,200, but for lower frequencies, it would be lower, then it would go higher. And you understand that if I have an even stiffer matrix with more voids, again, I would have here a different curve, but still it could pass from the same point, like the velocity could still be 4,200 for a certain frequency. There is also other type of cases, like, for example, you have a deteriorated matrix or very less stiff or soft matrix, but with very stiff aggregates. In this case, you could still have the same wave velocity for a certain frequency band, but of course the material is totally different in that case. This can happen, for example, when you have a severely deteriorated concrete from a chemical sulfate attack, and you have low stiffness matrix, but the aggregates are still not much influenced, and therefore they give you this negative slope of dispersion. Therefore, you understand that if I want to go for very delicate information, I would like to have also information of the different frequencies to make the velocity measurements for a band of frequencies as big as possible in order to understand what is the reason for the behavior that I am looking at. Obviously, if the deterioration is so strong, then the velocity itself will drop much, and therefore it will be evident even by pulse velocity without me caring much for the frequency. But if I want to go early and early in the damage in order to make as better as possible prediction of what's going to happen, you always need to extend a little bit to the frequencies. And here I summarize some of the results. These are first theoretical results. So as I said, when you have a material without any damage, without any void, your velocity will be constant for all the frequencies that you choose. How does this translate into experiment? Well, it cannot be absolutely straight, you understand, because it is experiment, and because concrete anyway, it is not homogeneous by itself. However, you see that it's a very, very smooth curve. Now, if I go to another case of chemical sulfate attack, you see that the trend shows downward slope, so the velocity drops with frequency, and this also reminds us these theoretical results of the deteriorated matrix with very stiff aggregates. And of course, if you go to the case of voids in a matrix, this is here experimental result. This was done when I was in Japan in the laboratory of Tomoki years back. So you have this trend, upward trend of velocity with the frequency, and it increases until it reaches the velocity of the matrix. So you see that if I can have an evaluation of the velocity for different frequencies, then this would allow me to match the result with some kind of theoretical prediction, and then I understand what is going on in the concrete, apart from having a very general idea of the pulse velocity and a rough evaluation of the elastic modulus. So this is something that it's very interesting, and of course it's easier to do in laboratory, and we are doing a lot of work about that. It's more difficult to do in practice, but of course there are still possibilities, and I will show just one indicative case later. So if we have our eye in the final application, then obviously we would like this to be air-coupled. The big advantage of air-coupled measurements is that you don't use coupling that is manually applied, something like a grease that it can create differentiation and variability in your result. And of course, it makes it less intensive and makes the scanning easier because you don't touch the sensor and therefore there is no friction, and it's easier to take a lot of measurements because usually you would need a lot of measurements to make a characterization, and it's easier to do it with a non-coupling sensor rather than applying grease and make the measurement, apply again grease, make the measurement, and so on. So of course this would be this would enable a very good application on the site. There are some groups that are working a lot, and they have done excellent work in the non-contact ultrasound field. What we want to do is to check if the previous dispersion curves that I showed you, they can be constructed, they can be calculated based on air-coupled ultrasound. Here, the problem is that when you have air-coupled measurement, obviously due to the gap of air, you have very low amplitude of the signal, and therefore this maybe implies that you don't have enough spectral content in order to make this dispersion analysis that I showed you to produce the velocity versus the frequency curve. So we started with numerical simulation. So of course, I will just let it to run while I explain because it's quite slow, but anyway, I will cut it. So you see the excitation here, the longitudinal wave, the shear wave that comes a little bit later, also the Rayleigh wave on the surface. And if you go a little bit later, you see also this diagonal wave, which is what we call the leaky Rayleigh wave. It's the wave in the air that was excited by the Rayleigh wave on the surface of our structure. We have here our receivers, which are inclined into the Rayleigh angle in order to get the wave as a planar wave and not have aperture effects. And then we can make the analysis between these 2 points to find, for example, velocity or to get the waveforms in the first place. So we have done that, of course, with air-coupled transducers that you see they do not touch the specimen. But of course, we also did it with sensors that touch the specimen in order to have the reference. So here you see the waveforms for the coupled and the air-coupled case. They are quite similar, as we can see. We see one strong Rayleigh cycle for each sensor. Of course, as you go far away, the amplitude decreases. You also even see the indication of the longitudinal wave that comes a little bit earlier. When we go to the air-coupled sensors, we see more or less the same thing. However, of course, it's even lower in amplitude and a little bit delayed even further because you have this extra air gap that the wave needs to propagate through. Obviously, we did that for different cases of heterogeneity, and I just show you here one example with a vertical cracks, as you see. Again, here is the Rayleigh wave. Here is the leaky Rayleigh wave on the air that we are going to receive with our air-coupled transducers. And then here are the waveforms, again, for the coupled and the air-coupled. This is a simulation result. You see now that we don't have just one big cycle, but the energy has been distorted. It's dispersed to more cycles, like 2 or 3 cycles. Especially for the sensor 2, which is the furthest away, you have the accumulation of all this scattering, and therefore you see many more cycles. Now, we want to see if the spectral information is still there in order to make the phase velocity calculation. This calculation is described in this paper. It's not a very difficult procedure, but you just do the fast Fourier transform of your signals. You get the phase information, not the magnitude that we usually apply. And you see the difference in the phase information between the 2 transducers. This phase difference depends on the velocity of the medium, and therefore you can find the velocity for each of the frequency components of the Fourier transformation. And here I show you some results comparing the coupled application, so the normal transducer that touches the specimen, and the air coupled that is with some kind of distance. And you see that the results are quite close. They are in a good agreement. And also that in some band, quite a big band, they are even identical. If I go to the case of the vertical cracks, again, I see the same thing. Of course, the dispersion curve has now changed much. It dropped, obviously, because we are talking about a deteriorated material with discontinuities in this case. But you also see that it's quite in good agreement between the air-coupled and the coupled. That is a very promising message, let's say, that it can be, all these delicate measurements can be done even with air-coupled transducers, and the information is not lost because of the propagation through the air. Another thing that is very important, apart from the drop of the general level of the velocity because of the damage, is that you have some areas with very strong dispersive phenomena. Like, for example, here you see a big slope of the velocity increase, and then a local peak, and then it drops again. Where you have this strong effect at those frequencies, they correspond to a wavelength that is characteristic of the damage pattern or the heterogeneity pattern of your material. So in this case, here it's 17 millimeters, the wavelength, here approximately 17 to 20, let's say, and the cracks that we had inside were 12 millimeters. And also it's not only the crack itself, but the separation between the different cracks that was about, again, 10 to 12 millimeters, I don't remember exactly. In all the cases that I have also found in the literature, when you have this intense dispersive phenomena like increasing very steep slopes, for example, or local peaks of your velocity versus frequency curve, the wavelength at that point is always a little bit higher, bigger than your heterogeneity pattern that could be the void itself or could be the separation between the different voids if you have a repeated pattern of heterogeneity. So in this case, it shows, apart from the general deterioration, also it starts to indicate what is happening in the material and what is the pattern that starts to be exhibited in the microstructure of the material. Here are some photographs of the experiment. Yeah, here is our pulsar. In this case, it's a little big, but it doesn't matter. It works well. Here is the foam that we use in order for any possible wave not to travel through the air directly to our sensor. Here is our air-coupled sensor. It's also tilted a little bit in the Rayleigh angle so that we don't have aperture effects. Of course, this is the specimen. This specific specimen was from chemical sulfate attack. And I think that, yeah, the sensor, I can say that it's called the optical microphone. It works with laser interferometer, but the laser does not hit the surface of the material. It is just going, let's say, back and forth in an opening of the sensor. And this opening is influenced by the wave that travels through the air. So the air under the excitation of the leaky Rayleigh wave has increases and decreases of the density. And obviously this changes slightly the refractive index, which is very important for the laser that propagates in this small opening. And therefore, this is how it can depict the wave that propagates. And this gives the advantage that you don't have resonances. It doesn't have any moving part. Therefore, it can have flat behavior for a very big band of frequencies, up to even 2 megahertz, which, yeah, in laboratory, maybe someone can utilize. We do this type of measurements right now in cooperation also with the University of Ghent. Here is just one example of the dispersion curve without freezing thawing cycles, and then with 30 or 60. You see, of course, that the velocity drops in general, but also that you start having some strong resonances that may indicate what is the type of heterogeneity that starts to be developed based on the wavelength. And also, this is the result that I also showed earlier. This is for healthy concrete. It's air-coupled measurement. Also, this is an air-coupled measurement for the chemical sulfate attack. And we try to do that both through the thickness and also on the surface of the material. Now, obviously, we do that, and it's very interesting to do for deterioration, for durability loss. But we want to do it also for the inverse procedure, which is the repair, or in this case, the healing of the material. So we have specimens that we break, and then we allow them to heal in the wet-dry cycles. So in water and outside of water periodically every day. Obviously, the concrete itself has self-healing properties, but we try to trigger this more by putting some kind of admixtures like the super absorbent polymers that they catch water and they release the water gradually in order to increase the hydration of the, or the delayed hydration, the hydration of currently unhydrated cement particles. And of course, we also monitor the crack from the surface by the microscopy. And we also do through the thickness measurement with ultrasonic transducers. We have done that a lot manually, point by point, but we also now started to do it with air-coupled transducers. So first, I show you some results from the microscopy. Obviously, when you have a crack, the initial crack is like 150 micrometers. This is what we target. And then as we allow the healing to take place, you see that for specific later days, the crack starts to heal at some point. We don't see the crack at some points, some other points we see the crack. In general, there is a decrease in the opening of the crack. In this case, for all the mixtures that we had, it's like half the original, from 150, like goes to 80. There are other mixtures that can even heal 100%. But of course, for me now, it's not the important point, the healing itself, but it's the monitoring of the healing. And what we see is that if I show you now the ultrasonic results, these are the mappings of all the measurements that we had point by point. It is not tomography. This is much simpler. Tomography, I think you will see later in 3D impressive mode. You see here the relatively homogeneous structure of the specimen before the crack. The velocity is like 4,000 to 4,500 meters per second. And for all the different mixes, you see the average was quite high at that area, at that level. When we crack it, obviously, we see much more red and yellow because there is a discontinuity between the sensors in the middle of the specimen, and the velocity in average drops. But of course, then it starts to increase day by day after we apply the healing. The healing cycles, the wet-dry cycles, until the 28 days that it's quite well restored. Some of the mixes had even very high restoration, close to the original value. When we had subs, usually the restoration is a little bit higher, so they promote the healing. But you also can see, apart from the average value, you can also see the heterogeneity of the healing itself, some places more than others, for example. And this is also good in order to understand what is the healing process, if it is uniform or not. So this is one application that we would like to do in air-coupled mode, but of course also to try to check different frequencies, as big band of frequencies as possible, because, you know, there will be a frequency that will give you the best results. So the biggest drop when it is fractured and the biggest restoration when it is healed. Therefore, if you search several frequencies, it will be helpful in order to optimize your result. And as I said, this is quite easier to do in laboratory rather than in real practice. However, I will show just one example. I think that Tomoki will expand more to the structures, but I just wanted to show that it is still possible to do scanning of frequencies in specific cases in the structure. And I take this example from a bridge that developed some through the thickness cracks, and then they would repair them by epoxy injection. It was manual repair in this case. So we applied sensors from the top of the deck and from the bottom. The crack is somewhere in the middle. And we made measurements. You understand that the paths that are not influenced by the crack will have a bigger velocity than the paths that are cut by the crack. It's a discontinuity. And of course, that happens before repair. After repair, obviously, these paths would be much upgraded in terms of transmission. Therefore, you can do this tomography procedure separating cells. This is just a picture from the experiment. The crack was very, very small. However, it was still through the thickness of the whole deck. And here is the pencil lead break excitation that we use many times. And here I just want to show the tomograms for focusing on the velocity of the 10 kilohertz, the frequency of the 10 kilohertz, relatively low frequency. We obviously can see the crack before the repair, but you see that it's not accurately depicted because this is the opening that we could visually confirm. And of course, then we can see again the repair, the upgrade of the velocity. But look at the tomogram at 100 kilohertz, where we see a much better depiction of the crack based on the points that we could confirm visually, but also a bigger characterization capacity, a bigger discrepancy between the good concrete away from the crack and the bad concrete, the damaged concrete on the crack. Therefore, it gives you better characterization capacity and also better depiction of the shape of the crack. And of course, later you see again some kind of residuals from the crack because the epoxy that is being used, although it's very strong, it still has much lower elastic modulus than the concrete itself. Therefore, the velocity will not be expected to 100% restore, but again, it's restored to a very high percentage, something that is already enough for the engineers to continue the construction. So I think that I am close to my conclusion. I can say that the ultrasound in general, as we know already, offers relatively easy. I say relatively easy because I repeat that if it's just one specimen, it's easy to measure ultrasound. But if you want to do it in a large structure, obviously it becomes much more complicated. It gives you a relatively easy and non-invasive assessment of the stiffness of the material. Also, checking various frequencies or bands of frequencies as big as possible offers much more characterization capacity. Obviously, the ultrasound is sensitive to damage, but it also is sensitive to the inverse of damage, which is the filling or the healing, or in general, the repair process of the structure. Of course, the ultrasonic mapping can reveal the zones that you have more or less pronounced healing, but also more or less pronounced damage. And then one point that I find very interesting research-wise, and hopefully eventually for the construction site, it's that the dispersion curve calculation that gives a lot of information for what is really happening into the concrete is also possible to obtain even in air-coupled mode. And this is something that we try to advance more and more. So generally, I'm not advocating in favor of high or low frequencies. It's just that you can check the different frequencies in the band that it's possible that you expand, and then this will increase the characterization power. So I would like to thank you for your attention. Thank you again for the nice invitation. And of course, I'm here for any question or any discussion that you would like to have. Thank you.
Thank you very much, Professor Aggelis. So let's move to short Q&A. There's a Q&A box question is coming. One question from audience. I read. What is the fineness of crack that can be detected by this ultrasonic method? And is there any way to identify the different crack files through this method?
To identify the size of the crack, or what was the question exactly?
What is the fineness of the cracks that can be detected?
Okay. Well, this is a very difficult question because it has to do with a lot of different parameters. The crack itself has has a certain shape. From one side, maybe it's thin, but from the other side, it's very long. So it depends on how the ultrasound will reach the crack. If it reaches vertically, then the crack may be very thin, but still we can be able to measure it to see the reflection. If it's on the same side, then it will be much more difficult. I think that when you have a big crack, it will be quite easy. Big crack in the measure of the wavelength. So if we have a crack that is similar to the wavelength, it cannot go unnoticed. If it is smaller, then the chances increase that it goes unnoticed. But of course, the crack will not be by itself. It's not just a small crack. Maybe there are many different cracks. And therefore, in that case, you would see these scattering effects that I was talking about. For example, when you have a lot of freezing thawing cracks, they start being very small. They can be like, the length of them could be like millimeters at the start. This could be smaller than the wavelength, but still it is possible by the scattering interaction to identify that there is a lot of cracking inside. So it is always a very complicated issue, but I can give you, if it's like one big crack, then the order of the wavelength could be enough to measure it. If it's smaller but a lot of cracks, still it's possible by the scattering interaction and the different dispersion.
Thank you very much, Professor Aggelis. Other question is coming, but time has come, and other questions discussed in panel discussion. Okay. So now, thank you very much, Professor Aggelis.
Thank you.
Thank you.
So I stop sharing.
Yes, please. Thank you very much. Okay, let's move to the next presentation. Okay. Next presentation is from Professor Tomoki Shiotani from Kyoto University, Japan. And he also has many research achievements and contributions, so I will introduce his biography as briefly. I show the slide. Professor Tomoki Shiotani was serving as chair of both the AERTC of Japanese Society of Non-Destructive Inspection, JSNBI, and the Acoustic Emission Working Group, AEWG USA, and he is president of the International Institute of Innovative Acoustic Emission, IIIAE, organization comprising three prominent A groups from Japan, USA, and Europe. He also played a pivotal role as a convener, leading the successful publication of 3 proposed ISO standards on A testing in 2019. And he has gained recognition with 4 NBT awards from the Structural Faults and Repair Conference, UK, and in 2008, 2012, 2016, and 2018. He is a distinguished medalist of the AEWG in USA, the 4 award in 2013, the Joseph Kaiser Achievement Award in 2017, and the gold medal, the highest honor bestowed by AEWG in 2019. And his research area encompasses advanced NBT for assessing critical infrastructure such as road bridges, dams, tunnels, and more. His primary fields of expertise revolve around advanced NBT with elastic wave methodologies, such as USDW tomography and acoustic emissions. Impressively, he holds 49 patents, including 18 of international significance. Okay. So let's go to the next presentation. So Professor Shiotani, if you are ready, please share your slide.
Okay. Can you see this slide? Can you see this slide?
It's presented as vision.
It's okay.
It's okay. Thank you. Please start.
Okay, thank you very much, Dr. Terasa, for your kind introduction against me. So my name is Tomoki Shiotani, Kyoto University. So Dimitrios talked a very fundamental and very important aspect for elastic wave. As he said, the dispersion, he studied that dispersion 20 years ago, and we get together and study in commercial company 20 years ago, 15 years ago. But it's still the fresh subject for civil engineering, especially using non-discovered testing or elastic wave testing. Okay. Anyhow, my talk is much more on the material and structure things. As Dimitrios shows, the first part of materials evaluation was mainly demonstrated by him. And in my talks, I'm going to talk on some other timings applicable by NDT. That is, yes, structures or performance evaluation. For example, initial quality assessments of the concrete materials that can be evaluated by NDT. And for the crucial phase, repair phase, we try to assess or quantify the repair works with NDT to judge deep repair or renew the structures. So we established the TC269 IAM in Vrije that started 2016, dealing with damage assessment in consideration of repair and retrofit recovery. And for the general phase, we can apply the NDT to quantify or glorify the deterioration due to, for example, aging, harsh environmental conditions, and especially in Japan, we have suffered from natural disaster like earthquake, flood, and so forth. So at that time, we tried to assess the structures after that very big event with using NDT. For the initial phase, some of the pioneers have already applied NDT. For example, this is so-called famous robot, namely Rabbit, that has been developed in Latogas University. And the Gugansky, Professor Gugansky, summarized the recent points of deterioration in a specific bridge deck. And this is actually obtained the points against the conditions. And he tried to interpolate this to the 100% conditions, assuming that the initial phase, there is a completely healthy conditions. But as you can see here, that does show the quadratic curve, but showing, yes, cubic curve. So he just have the questions, but the initial condition is really 100%. That's implying us there's a possible damages even in the initial phase. So those same phenomena can be found in Japan. This is a case in my laboratories. We applied ultrasonic tomography to newly developed lightweight architect of excess highway. At that time, we have this kind of very beautiful lattice patterns. Yes, so this lattice pattern is corresponding to the location of river reinforcements. Yes, however, if it is a river, the P-wave velocity should be more than 5,000 meter per second, but showing, less than 3,000 meter per second. That's implying us there is a defect, damage, or voice. Those can be happening along the reinforcement, right? So this is the initial damages made by some of the big, how can I say, unexpected events. And for the repair phase, we try to assess the structures with using LDT. That's technical committee of Vrije has been started from 2016 and ended last year. So in this committee, we already have an outcome to end this standard. That means non-destructive inspection standard of JSNDI, published in September 2022. And we expand that standard to Japanese industrial. And the preparation committee has been terminated last June, and now moving to the draft committees. It's going to be established from this year. So we also submit 2 item recommendation based on the outcome of this technical committees. And the state-of-the-art report can be obtained by the Journal of Development in the Built Environment. The chief editor of this journal is Dimitrios Aggelis. Okay? And in the future, we're gonna move this standard to the ISO standard. Okay. So from now on, I'd like to talk on the much more general things or deterioration due to aging. So we try to assess or evaluate the structures by using non-destructive testing. So before coming into non-destructive testing, we're going to show you the important events in Japan. As you may know, in 2012, December 2nd, Sasago tunnel accidents have been generated. Then the concrete panel separating upper half and the lower half of the tunnel are being collapsed with a manner of chain reactions. The deterioration of the anchorage suspending this panel would be the main cause. By this timing, 9 people died and 2 injured. So we have the new regulations for the inspection of the infrastructures. In 2014, these kind of items have been regulated. That means all of the infrastructures have been investigated every 5 years with 4 health levels. The first one is intact, second one is proactive maintenance level, third one is early measure level, and fourth one is immediate measure level. Okay. So now I'd like to show you the recent results in 2019 and 2020 for the case of bridges ranked immediate countermeasure necessary. Okay. As you can see here, in 2019, 30% of the bridges is planned to remove, abolish, or completed to remove or abolish. The same trend can be found in 2020. Almost 30% will be removed or abolished. You know, for the case of rank 4, immediate countermeasure must be implemented. In that case, there's no repair. Just give up or discard. This is the actual level for the infrastructures. Now I'd like to see some of the bridge classifications based on owner's type. So this is a peculiar statistics in Japan. However, when you focus on the owners, the 4% is managed by Ministry of Land, Infrastructure and Transportation Tourism. And others, almost 94%, was managed by local public body. As you think, local public body, what is the characteristics of that? Yes, there's few skilled engineer and with small budget, right? Therefore, for this kind of the, how can I say, infrastructures managed by local public bodies, it's rather difficult to classify such a kind of complicated flow levels and repair or, you know, such a kind of judgment. It's very, very tough. So this is my ideas against the deterioration level, you know, with a function of time. So intact can be regarded at here, at the present standard. And the proactive maintenance level could be around here. And the final, this kind of phase, immediate measure level, they regard it. But for the case of the structures located in metropolitan area, I mean, it's very, very high risk structures. The intact conditions should be much more filtered, for example, around here. And more precise, how can I say, a judgment which will be sensitive to the damage to be applied, should be applied. And for the case of the low risk structures, mainly located in remote area, as I demonstrated already, we just say, you know, 2 extreme cases, intact or not intact. So with this kind of judgment, we can say, yes, remove it or leave it, right? And major classifications, the health classification should be established. That's my, how can I say, idea. And for the fitness for service, that is the term of mechanical engineering. Those can be varied depending on the type of the structures. For example, if we focus on the intact level or the metropolitan area, at this point, we try to see, right? However, for the low risk or remote area, until here, we can follow. So in this case, yes, different thresholds can be applicable depending on the risk of the structures. Then, corresponding to every single threshold level, we can apply, for example, for the metropolitan area, high-risk structures, super-sensitive MDT should be applied. And for the low-risk area, yes, less sensitive LDT can be applied, right? Then, as you know, the number of the infrastructure is highest for the low-risk area, remote area, and low in the metropolitan area. Therefore, we should solve this low-risk remote areas infrastructure assessment first, then try to move to the metropolitan area. Now, I'd like to show you the less sensitive NDT corresponding to the remote area. So this is the abandoned bridge, give-up bridge provided by Tokushima Prefecture. So we are allowed to cut this vertical member, and in this period, we are developing super acoustic sensor that are the super wideband frequency. We try to verify that sensors with using this vibration, depending on the progress of damage. Now, you can see the vertical members is cutting. Then, after cut, the two different weight of the vehicle with two different velocity have been passed over the bridge. Then we measure a waveform like this. And discuss it with the frequency. Now, we cut two vertical member. And for the initial conditions, yes, intact condition, I should say, like this frequency we can get as a natural one, resonant one. And for the half cut was implemented, the frequency decreased. And the second member was cut, more decrease can be found. After that damage, we recovered that by adding new plate with bolt. Therefore, slight recovery of the natural frequency can be obtained. So if we evaluate good or bad, this kind of simple idea can be applicable. So one of the example is made by the electorate energy harvesting systems. That was collaborated with this institute. As you can see here, this is the concept of electorate embedded in Japan. So there's two typical parts. The one part is fixed electrode part. The other is movable electrode part. With this manner, the electron can be moved along this circuit. And if we can put some condenser, the energy can be stored with that. As you can see here, if we can change the length, I mean the span, the frequency of generation would be adjustable, right? So we apply this device to alert the damage. This is a very, very simple laboratory experiment. This is mainly done by Chun sensei in Kyoto University, collaborated with Saginomiya Corporation and the University of Tokyo. This is the experimental steel bridge with intact case and damaged case that can be reproduced by this notch. Okay? And yes, this is the damaged conditions, and this is healthy conditions repaired by this metal plate. Now you can see this is the, how can I say, model vehicle passing over the bridge. Okay. Then three-dimensional accelerometers has been placed onto the support. Okay. And for the both case, health state case and damage state case, we monitor the acceleration. Now you can see two typical frequency spectrum for health and damage case. And we focus on this frequency, that means 204 Hertz. For the healthy states, there's no peculiar, how can I say, components at this frequency. However, for the damaged conditions, in 2004 Hertz, there's a peculiar component. Therefore, corresponding to this frequency, Saginomiya Corporations devised a vibrational energy harvesting systems with LED. So this vibrational energy harvesting system can be stored the energy corresponding to the 204 Hertz vibrations. And if it reached a certain level, LED can be blinked, emitted, right? Now you can see this is a case for healthy states. Even with energy harvesting device, there's no emission. There's no lightning. However, for with 204 Hertz vibration, yes, LED can be blinked. So this is a very, very simple device, but they can provide us this is good or not good. Okay. So now I'd like to move on to the slightly sensitive NDT. Yeah, this is just a concrete bridge deck, and we're gonna focus on this panel B, and we put acoustic emission sensors, and we have a tomography approach. We have acoustic emission sources as a tomogram at this moment. So this is 5 days monitoring result in terms of acoustic emission sources. As you can see here, a bunch of acoustic emission sources can be obtained through this monitoring. And this is a tomogram velocity distribution of wave wave for the bottom area, upper area, and middle area. As you can see here, the central area have been damaged because there is a low velocity can be obtained. Okay? Then with acoustic emission, we already understood that if there's a less emission and a low damage, that should be seriously damaged. Okay? As you can see here, in this area, low emission and low velocity area, there's a serious lateral crack solved by the cores. Now, much more simplified evaluation can be possible by using naturally dropped phenomenon. This shows the acoustic emission activity with elapsing time, almost 5 days, on 120 hours. Okay, so around here we have a very intensive acoustic emission activities. Now you can see this is a humidity along the same time scale. At this period, actually torrential rain can be generated. Okay, Therefore, high emission was mainly done by tapping by precipitation. Now you can see this is the 5 days acoustic emission monitoring for that bridge deck. And this is the acoustic emission sources during 700 seconds, almost 10 minutes by precipitation. So now you can see almost same pattern can be found, both the long-term monitoring and 700 seconds monitoring by water droplets. Now, this is the pattern of water droplet source location, even with evenly distributed heat onto the surface of the bridge deck. There's an empty area, right? So this is a core sample result. And this empty area, there is a huge or serious lateral crack, okay, generated inside of the concrete bridge deck. So with this interference, evenly generated acoustic emission sources onto the surface cannot be propagated to every single sensor. Therefore, with using the empty area, we can roughly evaluate the seriously damaged zone, especially damaged by lateral crack. So that can be summarized by active methods of LIDEM recommendation. Okay? And for the passive method, it's a little bit tricky, but with using acoustic emission source density and elastic wave velocity, as I already demonstrated, we can see that detail, damage degree, okay, by using this kind of mapping system. So those are, how can I say, issued by LIDEM recommendations in a couple months. So finally, I'd like to show you the sensitive NDT. As Dimitrios already demonstrated, normally we try to see the crack tip with using this kind of simple combination by pulsar and receiver with ultrasonic transducers. Okay, and if we know the geometrical, how can I say, arrangement, we can easily estimate the depth with these equations, because we know the arrival time difference or propagation time. Okay? However, for the actual crack, due to the existence of filler, such as dust or water, or in the other case, reinforcement, if the crack crossing the reinforcement, the tip will be underestimated than the real one. Therefore, we developed a tomography algorithm with using through the thickness waveform. So in this case, as Dimitrios demonstrated, we can see the internal cracking characteristics on the section, right? So with this kind of tomography approach, we first developed in 2D and 3D, and finally in 2017, we expanded that from ultrasonic waveform to acceleration level. Why we need the acceleration level? Yes, if we apply the elastic wave technologies to the substantial big scale of infrastructures, we cannot propagate high frequency signal. High frequency can be reached around 50 centimeter or 1 meters at maximum. Therefore, 10 meter scale structures, much more lower frequency will be necessary. Therefore, acceleration level is enough, okay, to apply. Therefore, we developed accelerations tomography in 2017. Anyhow, in tomography approach, this is the result of three-dimensional tomography. We can see the detail of the damage in every single area And I'm very proud of providing this damage detail to the bridge owners. But they said it's too much. We don't need this kind of detail estimation. We just know much more rough classification, much more rough sectioning. Okay. At that time, if they know, they demand 2 different cases, good or bad, and 4 times 4 section. That means 16. That means the case 2 to the power of 16 cases is only, how can I say, potential cases. So based on the measurement result, we try to search the most likely case with AI. This is a very, very simple case. No need for the complicated tomographic calculation algorithm. So those can be applicable also to know the repair area. This is the tomogram, velocity distributions. But if we say less than 3,500 meter per second area could be areas of repair, we can say, yes, here is a target of repair. So the classification and the, how can I say, resolutions of the measurement is very, very important. And that should be discussed before applying the NDT with client owner, right? Okay, these are takeaway in my talk. NDT can utilize several phases of life cycle in infrastructures. Initial, repair, and general deterioration phases we can apply. As for general deterioration phases, adequate NDT, where the level corresponding to measure classification determined by the risk of structures shall be chosen. In case of low, mid, and high risk structure, vibration measurement with energy harvesting, a measurement with raindrops, and elastic wave tomography approaches are the candidates respectively. Thank you very much.
Thank you very much, Dr. Shiotani. And let's move to the short Q&A. Then comment. So I'd like to ask about some point. So in the vibration monitoring, acceleration data in the healthy and damaged state, please show me the slides of about yes, yes, that's right. Sorry, I missed it, but what meaning of frequency of 204 Hz?
This is the, how can I say, frequency spectrum
Yes.
measured by accelerometers. Okay, and for the case of health state, without any notch, without damage, and this is a case with notch. I mean, this is simulation of damage. Okay, so at that time, for the only damaged states, there is a frequency spectrum at 204 Hz.
Oh, no, I see. And this the frequency of 204 Hz is in this specimen, right?
Yes, of course. This is just a example in the laboratory specimen.
Oh, I see. Then you can adjust the frequency to turn on the LED lights, right?
Yes, this is a case to put the sensor on the support, but depending on the location of the sensor placement, the frequency will be changed. Okay, this is not a this kind of natural vibration. This is just a sort of the vibrations at the support. It's different from normal vibration.
Thank you. And so now it's time to move afterwards the panel discussion. So thank you for Professor Shiotani.
Okay.
Thank you very much. Okay. Some questions already answered by Professor Aggelis. And okay, let's move to the next content. Okay, can share the slide again. Next. The panel discussion is topics we will discuss. I prepare is like this. One is additional Q&A for the presentation. Second is current usage of NVT as standard test in civil engineering. Research must cooperate as a research field to develop NVT and last fall the future vision about the application of NVT. So additional Q&A for the presentations. Is there any comment? Professor Aggelis, I would like to ask a question about your presentation. Okay.
Yes, please.
Yes. I'm very interested in air-coupled sensor. Yes, it's very interesting. But I want to know the distance from the air-coupled sensor and the surface of concrete. How long the distance can be measured?
Yes. So this is a very tricky point, because you should be very accurate in this, else the propagation through the small distance through the air will change a lot the arrival time. Practically, it doesn't have to be very big distance, like 1 centimeter or something like that, but you should be very sure about the distance, because imagine that if you have just 1 millimeter bigger distance, then this would increase very much your transit time, and you will think that your material has low velocity, although it is just the lift-off distance from the air. So we try to control that as much as possible. So we take calibration measurements earlier, and I have seen also other measurements, like I mentioned Professor Popovich from Illinois University, that they also have a displacement measure from a laser nearby the ultrasonic sensor in order to be very, very accurate. So it is an issue, and you should be quite careful about that, because if you don't know the exact distance and you have fluctuations in the lift-off distance, this could be imported into your results, and you would make a very not a correct interpretation. But practically, it would be something like that, like 1 centimeter. You don't want to have it too much, because then you have extra damping. You want to avoid too much of the damping through the air. Therefore, practically, it would be something like that.
Thank you very much. And one more question, please. The air-coupled sensors method is how big this spacing can be applied? in your presentation, specimen is 100 millimeter, 100 millimeter, right? And this is a laboratory test method, I think.
Yes.
If the specimen is more bigger, can you pick up the sonic
Yes.
as a couple from how long the
Yes.
input and output distance? Please.
Yes.
Yes.
This is a very important point. The transmission is very difficult from the air-coupled excitation to the specimen, and then from the specimen to the air-coupled transducer. One way to overcome this is to have semi-coupled measurement so that you can apply your excitation with a sensor that touches your specimen, but then of course you have sensors without touching and you have many receiver points. This is a very valid procedure to do, and all your acquisition is air coupled, and therefore it can be, but this is for the surface. If you go for through the thickness, I would say that so far we are experimenting with up to 10 centimeters thickness. So in the project that we have with the University of Ghent, we apply to the ultra high performance concrete, which is a concrete usually coming in slender elements like 5, maximum 10 centimeters. Up to that point, we can get a very good signal, and some of the results I showed some curves. For bigger, of course, it needs to be a different type of excitation. It is still possible, but of course, it's not the most casual thing to do. With higher thickness, you have higher damping, and therefore the percentage of the wave that will arrive to your sensor will be much smaller. But there are other cases with laser excitation that is also possible to use. But obviously, for big thicknesses, there should be an extra concern, let's say. Up to 5 or 10 centimeters, it is already possible.
So may I answer? From my experience, yes, I've ever applied this kind of air coupled one, and so many articles have been already published. So in terms for attenuation, 1 millimeters is 20 decibel attenuation. As Professor Ono of UCLA sent me the papers on that.
Well, I can also add something in here. Okay. I don't think that it's so severe because we have movements in the area of a few centimeters. It doesn't change so dramatically. I think that the biggest problem is the impedance mismatch that does not allow the wave to go from your concrete to the air. There you have like 99% reflection, and therefore, in my opinion, this is the problem, that not much energy escapes into the air. We have done measurements from very small distance, 3, 5, 10 millimeters. There is, of course, a drop in the amplitude, but it's not as severe like 20 decibel per millimeter. Maybe that was also referring, including the transmission between the two materials in the interface. But as to the air itself, it's not so severe, the problem, let's say, of the damping.
Thank you very much. Okay, so thanks. Next question discuss about the second the current usage of LBT as a standard test in civil engineering, and I want to ask about this topic. And this means in today's presentations, Professor Aggelis and Professor Shiotani taught us some new methods of non-destructive test. And then I wonder how to make people aware of and use these new NDT technology. And
Yes.
as you are both have been involved in standardization of NDT method is important, I guess. So how to make people to use these methods. So please give me some comments about these topics. So
Yes.
please,
Like me to start, or Tomoki?
Yes, yes, yes. First, I should show you the most primitive ideas for NDT as a routine inspection is visual inspection. We try to see close look and try to see the crack width. That is the one of the first step of NDT. And the other, NDT is try to listen to the sound by tapping. This is, another typical case of NDT. And if it is much more advanced, we try to measure it or record it with some special devices and try to do it with wavelet transform or the other, sophisticated algorithm. So anyhow, visual testing and tapping testing is very, very two representative LDT or routine work. Are there any sophisticated also? Dimitrios, put some additional idea.
Yeah. So about this, it's obviously a very important topic. When we do experiments in laboratory, we have a standard specific equipment, we have specific operators, we have different conditions. Therefore, the experiments will not be repeatable from laboratory to laboratory throughout the world. They could all have common trends, but they cannot really be repeatable in the sense that they could be applied in practice. On the other hand, if you want an advancement eventually to reach the practice or the construction site, it should most of the time be applied by some kind of company, so industry. Therefore, the industries are very fond of the standards because they want some straightforward procedure and they want to rely on a standard that they have used. Therefore, standardization is quite important in making the advancement penetrate into the market and of course into the actual use. Obviously, there are not so many standards in all the different types of tests that we do, but there are already some, like in the ultrasound. I already showed one table for the ASTM C597, which is for ultrasound application. It has the steps, how you will apply it, what will be the thickness versus the wavelength, how you measure the velocity, how you can project to the strength, for example. Also, there is a standard about the rebound hammer. You can also check the surface hardness and then project to possible compressive strength. Other standards as well for the semi-destructive measurements, like this capo test or the pull-out test that you can find. But of course, it's not always, there are no standards for all of the different techniques. This is a very tedious procedure. That is why, as you saw, Tomoki is leading in this type of recommendations and these practices committees in order to create standards. And I think that this is the only way that any advancement could go into practice. It will take always a lot of time, and it needs a lot of confirmation, a lot of scrutinizing, a lot of experiment before something penetrates into the standards, let's say. But I think that it's the necessary procedure for adoption in the actual construction and be used from the companies.
Thank you. So, as you mentioned, the making standardization takes a lot of time, I think. So,
yes.
But the derivation of complete structure has been now going, and how to the and try and error is another way to promote this method, new method, I think. But
Yeah, one of the most important things is, you know, as Dimitrios and I, there's a very big gap between laboratory specimen to institute specimen. You know, 10 centimeter, 1 centimeter thickness, yes, mainly any NDT can be applicable. But for the 10-meter thickness, 10-meter height, only, you know, several NDT can be applicable without any high frequency, for example, in terms of elastic wave technologies. Therefore, if we seriously want to make a standardizations for civil engineering by NDT, we should first, what kind of NDT could be possible to apply to the realistic structures to study first. Then coming into the middle scale and small scale. But for the small scale specimen, they are dealing with gigahertz, terahertz, megahertz. That cannot be applicable to the real world. So very big gap are there.
I feel so. Today's Professor Aggelis presentations using a very high frequency. So, but this is very interesting. So, yes, thank you.
So in laboratory, because we have the possibility, we can extend, of course. In laboratory, the important point is that you can understand the mechanics of the propagation, the underlying principle. That is why it is okay to expand to the biggest possible area, because you know all these different levels of heterogeneity will have an effect at different wavelengths. Therefore, you can study the material very well, scrutinize, let's say, the material in any detail you can, in order also for the development of the material, to find the ways that you can make the material better. Obviously, then there is a big filter and only a few things can be applied. And I can make let's say, what Or mentioned. I was talking some weeks ago to Nasos Anastasopoulos, who is very expert in the NDT of wind turbines. And he has done so many acoustic emission tests in turbines with many, many sensors. And then when they try to apply that on the site, they use only one sensor. Because this is practical, they cannot have too many sensors and they cannot interpret all these different ideas and different data that they get. Therefore, we understand that you need first to do a very good laboratory study for your material, for your process, for example, self-healing, understand how it works, and of course, then see what can be applied in practice and try to expand it as much as possible. But of course, it's correct what Tomoki says about the gap between the laboratory and the structure. And I think that there's always going to be a gap. It's inevitable. The standardization is somewhere in between.
Okay. Thank you very much. And the next topics, we go to the next topics. Some topics is must collaborate other research fields to develop NDT. This means I think nowadays we can see new technologies all around us. For example, AI, artificial intelligence, or digital transformation, and so on. So I wonder that to develop NDT for civil engineering, we should learn from other research areas outside of the civil engineering. I think so. Okay. The question is, are there any other research areas that you are focusing on? Could you tell me your idea about this topic? So please.
Yeah. So I can just start for this. Obviously, there needs to be some kind of collaboration. And, you know, in this type of discussions or presentations, people expect everybody to say we should collaborate, we should all work together. In this case, it is anyway obligatory, because it is very difficult for one person or one group to know everything. Because as I say to my students when I present about SHM is like a puzzle. And yesterday I was also having a discussion with Mike Ford, who made a presentation for our students here. And he also talked about the SHM jigsaw puzzle. So there are so many different pieces that you need to fit together. Obviously, someone can be expert in the sensors, someone can be expert in the interpretation, but if you cannot apply the sensor on the field, if you cannot power it, so someone should have the energy harvesting, for example, expertise. Someone could also have the expertise in the transmission of the data, that you need some certain speed. You cannot have so many data and just not be able to transport them. So you need also communications eventually, wireless transmission of the data. So I think that it is anyway obligatory. It is difficult for one laboratory to do everything. That is why it is also good to have consortia with people of different expertise. Because, you know, if you have one development in one field, this is very difficult to be applied eventually, as we already said, because you need developments in all the other fields. If I have the best sensor, but I cannot interpret the data with a new algorithm, with an AI or with machine learning, then how can I use it? Or if I don't have the power to use for the sensor, if I don't have the battery technology, for example. Therefore, it needs the different developments. And that is, of course, the interesting thing about SHM. But on the other hand, it's also the difficult thing, because you should have advancements in all the different fields in order for a global advancement to be there. In my laboratory, I can do a very good advancement. I can find the finest crack, but of course, I need many other people to support before this can be done in the structure. And also because you mentioned the AI and the machine learning, because it's also a very modern term, I think that it is necessary, because we get more and more data that we need to identify. And when you get the data, maybe with your experience and your background, you can understand the physics behind it. Why do I have a signal like that? What's happening? But there are underlying trends or hidden trends that you cannot understand by your insight or by your background. Therefore, it would be very welcome that we use more and more dedicated algorithms. Now they call it machine learning. When I was a student, we used to call it pattern recognition. We still used neural networks, nearest neighborhood classifiers and other stuff. And I also think that here, one crucial point is that we should engage more young people who are very handy with AI and all these gadgets, because, you know, the older people, they can be excellent at some specific domains, but the new technologies are tilted towards, you know, AI and automatization. Now, for example, I see my son who is 9 years old, and he sees a picture, he says, this is an AI picture. He already understands, because the young people are already embedded into this world and they understand much better than we do maybe. Therefore, I think that it's also crucial that younger people join the field, because they will have a much better potential for the analysis and for the machine learning.
Thank you very much.
Okay, from me, I can talk a little. I'm managing the very big consortium consisting of more than 60 organizations, and have a bunch of collaborations. I'm going to show you some of the collaboration research themes. One is the point cloud reproductions. That is collaborated with the computer science people in University of Illinois. And we are now developing the how can I say, super sampling machines. That is collaboration with mechanical engineering and electrical engineering guys. And the point clouds, we try to extract the surface crack. That is with using artificial intelligence, collaborated with data science guy. And for the aggregate sensing, we are now focusing on the sensing with energy harvesting and the automatic detection and the transmission that is collaborated with informatics guy. And for the materials like a CFRTP with fiber reinforcements and the fiber optics, I should say, that was collaborated with material science guy and aerospace science guys. So all those can be collaborated each other, but every single aspect we have a collaborations. So any multiple, how can I say, spheres, we need to collaborate, right?
Definitely.
Thank you very much. And Professor Shiotani, in your presentation, you mentioned about a small budget. Yeah, in a small budget, but regional region will have to maintenance their structure. So the new technologies combined to this problem, this thing. So,
Yeah, I mean the how can I say, the infrastructure located in remote area that is mainly managed by local body and the character of the local body, few skilled engineer and low budget. So at that time we don't need to apply sophisticated NDT, but as I showed, just a simple energy harvesting sensor with a blinking function will be one of the easy to just use or not to use.
Thank you very much. So I have let's move to the last topic, the future vision about application of LDT. So in today's presentation, some topics have been mentioned already, but once again, I would like to ask you about the future vision of LDT or your future work, please.
Yes. So I can also start saying just a few things. Well, it depends on how far future we are talking about, because if we think about a very deep future, maybe then we would have robots that would check the damage and also make the repair. We have already some glimpses of this future. There are, for example, the drones that they have camera, they even have infrared camera, and then they take photographs. And then there are researchers working on algorithms for automatic recognition of damage through the pictures. And then you could do maybe very fast some kind of assessment. So in the future, it can be much more automated. However, I don't want to be, so optimistic immediately, because I know that everything happens step by step. So we should hold, let's say, a small basket, but we should try to have just improvement on our own field. If I can extend a little bit more the frequency, for example, and I get a better characterization, it's good. If someone can have a better energy harvesting mechanism to increase the power, the autonomy of the device, it is also good. If you can have a better transmission speed for your data, a little bit better, it's also good. So I think that the combination of the different advancements in the different fields will give a better image and a better capacity for the SHM in the civil engineering. But of course, it's not something that will just come as an avalanche from one day to the other. It needs consistent work from the different fields, from the different players, let's say, the different people and laboratories involved and the companies, in order to improve the characterization and the application in the real field.
Dr. Terasa, can I share 2 slides now?
Oh, yes, okay.
Okay. Okay, I'd like to show you this. Can you see?
Presentation vision. Presentation vision. Yes. Okay.
No, it's okay.
Okay.
Yes.
Okay, so this is the, how can I say, ideal applications of the NDT. So we try to trace the life cycle of the infrastructure with 3 indices. The one is the money, one is the green things, the other is outside and internal informations. So for the internal information could be obtained by NDT. And how can I apply that NDT? Now you can see, this is a point cloud digital twin integrated with homography result. Also, the extraction of the cracking are also overlapped onto the surface. Now you can see we have a tomography around here, and gradually you can see, yes, these are velocity distributions completely over matched with these point cloud applications. So based on this kind of ideas, we can estimate which portion should be investigated for the next phase, or we can, how can I say, back 5 years ago's result with using this kind of, time span. So this kind of, visions, velocity distribution or LDT result incorporated with point cloud is a very, very crucial for the future vision of NDT. Okay, this is a collaboration result with University of Illinois, Urbana-Champaign. That's all. Thank you.
Thank you very much. And so the time has come, and we close the panel discussion. Yes, thank you very much. Your so impressive presentation. Okay. Okay. So at last, let me announce the next FCT seminar. We are going to have the next webinar on August 7th, 2024. The topic is about 3D concrete printing, inviting Professor Victor Catherine and from TU Dresden and Professor Minoru Kunieda from Gifu University. I look forward to seeing you at the next webinar again. Thank you so much for joining today's webinar. See you soon. And last, information about questionnaire and certificate of attendance of this seminar. We would appreciate your participation in filling out the questionnaire below the improving the JSCE concrete committee webinar. The forms is on the comments. Forms is at comment, and if you need certificate of attendance, please indicate so at the end of the forms. And the application deadline is set is 11 a.m. Friday, April 19. JST 6 p.m. Friday, April 19. Yes. Okay.
This seems to be a very interesting next seminar with very renowned people. I will definitely try to attend if possible.
Yes, thank you very much. Okay, the time has come, and let me close this webinar. I appreciate Professor Aggelis and Professor Shiotani and all participants. Thank you very much for joining us for today's webinar. We appreciate your participation. Thank you very much.
Thank you for the invitation. I appreciate
Thank you very much.
to be part of this seminar. Thank you. I enjoyed
Thank you
it.
very much. Me too.
Thank you very much.
Bye, everyone.
Goodbye, everybody.
Bye.